Okay, good morning again. We are in the last phase of our crypto journey in this course, of course, right? Normally, in many universities, they are full course on crypto, but it's a part of it. So, the part of our course, so we cannot afford to spend too much of time because now we'll move on to other topics where we will use crypto. Okay, like all internet protocols that we use, right? Or even we are using right now. Okay, we'll use crypto. For example, HTTPS. When you browse a website, you should always use HTTPS instead of HTTP because HTTPS uses encryption. Yeah, all right. Okay. So now let's move on to. So these are the references. Yeah, as I suggested earlier, please go through this particular reference of Professor Dan Bonet's. He teaches crypto course in Stanford. It's lovely course, and this course is available online, as I mentioned yesterday. Okay, and they have written a lovely book on crypto. Okay, so click on this page, you will get get this textbook. I have used some contents from this place as well. Okay, all right. Okay, so we will study these topics. We'll study about public key encryption infrastructure, public key infrastructure, which we call it PKI, and then look at some of the applications of digital signatures. We'll look at some raw certificates. Certificates can also be malicious. Okay, malicious in the sense that malicious party can issue a wrong certificate. Okay, or somebody can hack into system and then issue a certificate which is uh, for without any check. It means to some fake website, right? Okay, and then something that we'll cover if time permits is digital envelope. So this is where we are. We have completed all this. Symmetric key encryption, we completed everything, almost everything, like one-time pad, block ciphers, MAX, RSA, LGAML, then asymmetric key encryption, or we call as a public key also. And then we have looked at digital signatures. Okay, and now we are into the last phase, which is a PKI. What was the motivation for PKI? Okay, before PKI, we'll come to that. We have looked at digital certificates. Now note that there is a difference between digital signature. Sometimes people get confused between two. Digital signature is about like your signature, right? You're signing on a check. Now instead of a check, you have a file or document or something, which is of course in binary, and you are signing, you are taking just hash of that, and then using whatever you get as a hash of say your file F, okay, or message M, that's better, hash of message M, you get basically small, whatever file size, we know that hash is very small and is a one-way function, so from hash you can't get file, and then you use public key encryption. Okay, say RSA encryption, for example, you do using private key SK of whoever, say Alice, and on this content H of M. This becomes a signature. Now signature depends on what? Unlike your signature that we do on a paper and on any check or paper, here the signature depends on contents. Okay, so what are the contents? Here the signature will be there will be some signature, and if you change small a single bit, then signature will be different. Now in order to this thing to work, you have original message M, and then signature that you have created, signature of M using your, or using, Alice's, for example, private key. Now of course I am writing M here, but doesn't matter. SK Alice, and you send these two things to, from Alice send these two things to Bob. What Bob will do? Bob will receive, say for example, M dash. Ideally, M and M dash should be same, and get this signature, right? So let's call it S sig. Initially is, well, let's call it, outcome is S sig Alice. You get sig dash Alice. Now you have, or Bob has received this. Now he has to work on finding out whether signature is good or not. What he does is has takes this M dash and applies H on that, because H function is known. Okay, and dash say some H output, some say H dash, and then takes the signature. Okay, sig of Alice, basically signature on this content M of, and then applies decryption using same algorithm. Okay, well, what the algorithm is? Algorithm say RSA or something. So it decrypt using Alice's public key, PK Alice. He does decryption and gets something, say H double dash. So if H dash and H double dash are same, then it's done. It means that document is genuine and is signed by Alice. Okay. Now Alice cannot refuse that she has not signed this document. So this document, although is visible to everyone, this is visible, right? So there's no confidentiality. But everything else is there. The integrity is there, because if somebody changes in between this, then we'll come to know, and also non-repetition. And also the source. That source of this SAM is Alice. This also comes under integrity, source integrity. All right. So this is what we said, right? Now, one challenge is that this public key is always transported from one end to another end, in general in any asymmetric key encryption. Because here, even in digital signature, to verify digital signature, Bob must know the public key of Alice, right? And somebody can in between change the, we have seen one case where Mallory changes the public key in between. So somebody has to vouch for, somebody has to tell that this public key of Alice is correct. Okay, how do we do this? So that is using, somebody has to issue a certificate, like your character certificate your principal will issue. Okay, your director may issue if you ask for, or dean may issue, or whatever, right? So now there is a CA. So the process is that Bob wants a certificate of his public key, will request the CA. Okay, and CA will, what CA will do? CA will look at the identity of this guy, Bob, get some, basically all the data will check and ask for public key, and then issue a certificate using his own private key. Okay, so the certificate comes to Bob. When Bob sends a mail to Alice, he also sends a certificate issued by CA. Alice will receive this certificate. Okay, and then Alice, and this is encrypted by CA's private key, right? SK, SK of CA. Okay, and then Alice will use CA's public key to decrypt this, and then she will get the contents. Okay, done. Good. So now Alice will have genuine uh, public key of Alice of Bob. Okay, all right. So this is the mechanism we have seen. I'm revising it again. So this is a certificate that is to be created by CA. CA, now only few fields are shown here. Bob's ID, for example, he issues certificate for Bob. Okay. What will he do? He or machine will do, right? I mean, you will look at all these things like Bob's ID, Bob's public key, okay, and he will put his own information of his ID or whatever, and then this becomes part of the certificate. This is in plain text, and all he does is that he does hash of this. You will get this one hash code, okay, and this, and then what he will do is that he will sign using his own private key. So this becomes signature. Now this signature of course has depend on all what? All these contents. Okay. When Alice receives this, what will she do? All this part is in plain. Okay, plain text. She will take this and will do hash of that. This hash and the hash here which CA does is the same, because this hash function is all published. Okay, it's known, and then she will get this code, and then she will look at the signature and then do the decryption using CA's public key, and she will get this one. Okay, this content, and if these both are same, then all this is genuine, including Bob's public key. So that's the process. Simple. Okay. Now the question is that this is having one CA is not a scalable solution. Okay, so there is a hierarchy of CAs, and now you should look at in internet how many such CAs are there. Okay, and then there has to be trust among all these CAs, right? And there must be some hierarchy. Okay, in any organization it cannot be flat in this way, right? Somebody must be most trusted person, and even in, you see in spiritual organizations like ISKCON or whatever, or even churches, right? There is always a hierarchy starts from top. Like, you can see there is a pope who is he works from Italy and somewhere, and then there is a, all different countries, their heads, and then within cities there is, so there is a whole hierarchy, and there is a delegation of responsibility. Okay, similarly in PKI there must be head CA or most trusted CA, and then he will create hierarchy, and this hierarchy can be created anyway, right? I mean, maybe tree or maybe some other structure. So what I have shown here is a tree structure. Okay, but could be any structure, right? But only thing is that this most trusted CA, this is, then he will delegate responsibility to some next level CA will delegate responsibility further CAs, and so on and so forth, right? So this kind of structure can be created. Now when Alice is here and Bob is somewhere here, what all certificates are needed? Alice has, well, let's assume the Alice is here, for example, and this is CA number 1. So Alice will take certificate of CA1, certificate of her public key from CA1. Okay, so she will get this certificate. Okay, but who knows CA? Bob doesn't know CA1. Bob only knows his own CA, and then this is the hierarchy. So now Alice needs to attach, this all other certificate, which are basically CA1 must take certificate from CA2. So this is certificate of what? Certificate of CA1's public key. Okay, and then this CA1, CA2 is also not known. It is not Bob's hierarchy. So you must take certificate from head CA. So basically, Alice now has to attach all these three certificates, and Bob then will start using these certificates. Okay, all right. First, okay, so Bob will know possibly public key of head CA. Then from there he will know that CA1's CA2's certificate is correct, then CA1 certificate correct, and so on and so forth, right? And hence Alice's public key is correct. Okay, so that's the way it works, right? So now this thing is something that we already discussed, because we need hierarchy. Single CA will not work. All right. Okay. So this could be one hierarchy. So all users must trust root CA or head CA, as we discussed earlier. The proper terminology, root CA. Okay, root CA. So Alice trusts root CA. Bob also trusts root CA. Then this life is simple. There's the one certificate of Alice's public key by root CA is good enough. So Bob must trust. However, if the communication is between Alice and say Dan, then what all is needed? Okay, then Alice can just attaches the certificate issued by Bob CA. That's good enough. Okay, but how Dan will work in this case? Think about it. Dan knows public key of this CA, and this CA's public key must be certified by root CA. So when this CA will send to Dan his own public key, which he may publish, and the small CA's public key certified by root CA. So this certificate he must attach. Okay, this is how it will work. Okay. Now in the web browser, how will it work? Your web browser will must have, from any website is communicating to, any server is communicating to. Okay, the first, I mean, of course, when we study web technologies, if we get time, then we'll know that we first phase is, of course, we are doing public key encryption, right? For exchange of keys, basically symmetric key. Okay, then how? So basically, if your browser is communicating with a server, then this server's public key browser will use public key of server, as we've seen in the RSA. Okay, what will happen then? Okay, this public key must be available to the browser, right? Okay, so this server, it means that how will it be available? The server will send this public key to browser, your browser, for example. But your browser must know that this public key sent by server is correct, because server could be a malicious server. So it will get verified by, it means that now the certificate has to be issued. Okay, and then it means that this server must also attach certificate from corresponding root server, and each web browser then maintains list of root CAs. There may be many root CAs, not one. Okay, and then it means that the public key of all these root CAs is available in your web browser, right? All right. So please, if you're interested, please read through, you know, this technology. Of course, if we get time, we'll go through web technology and then we'll look at all this. But note that obviously first phase is always between browser and server. Note that we are not doing peer-to-peer communication. It's always client-server model, right? And you understand difference between client-server and peer-to-peer, right? So client, in general, most of the time we use client-server model. Like, Amazon server or your Google server, right? And so on. So client, there can be any client, and say request to server and the server will respond back. Okay, all right. It's not both have equal importance like peer-to-peer communication. That's another technology, right? Okay, all right. Okay. So when there is a client server model, or your browser is communicating with the server, say HTTP server, here is HTTP client. Okay, and the world in between is extremely insecure or unreliable. Anybody, any routers in between can see your message, there can be malwares anywhere in the cloud or in the internet, right? So how do you communicate? How your browser communicate with server securely? That's the challenge. Okay, and the technique that uses exactly what we have studied, that we are going to use. There is no other technique than 3 or 4 that we have studied, right? And these are symmetric key. So initially, if the communication is going for longer period, then you have to use symmetric key encryption. And then of course, if you are using symmetric key, then shared key must be exchanged, shared secret key between the two entities. That will happen through asymmetric key. All right, there may be some other variations here, but basic technology is same. What will happen in case of your Wi-Fi? Your machine is communicating to your Wi-Fi router, okay, or Wi-Fi terminal. In between, anybody can see that, right? What is being sent, because this is not going over wire, right? If it's going over wire, it's more secure, but if something is going over air, then security must be ensured, because everyone can read your signals, right? Then it must be your only way to provide security to you is to encrypt the data that is going from your laptop to the Wi-Fi server. And what technology we are going to use? Exactly the two that we have seen. First is asymmetric key encryption to share the key among the two, and then symmetric key encryption because you are continuously doing this communication. Okay, all right. So now look at this case. So what we have exactly similar, right? I mean, we have hierarchies of CS. And then when somebody from here communicates to other, then the public key must be attached with a number of CA certificates. Say CA, yeah. Okay. This okay. This verification. Okay. Bob, where is Bob? Bob is here. Bob trusts CA0. Bob trusts this because the root CA. Everyone must trust. Okay. Okay. Bob. So Alice sends to Bob certificates of public key, her own public key that she has generated, certified by this guy. So there must be one certificate, or where is Alice's public key is certified by CA1, we call it CA1, and then this guy's public key certified by the CA1 public key certified by CA X0. Okay. Now Bob says Bob trusts this, so I will now trust Alice's public key. All right. Now there are multiple trust anchors or multiple, as we have seen here, right? There are multiple root CAs in internet world, and so there are approximately 150 root CAs on internet. And these public keys of these root CAs, because you are communicating with an entity, we don't know where the entity is and who has issued public key to that entity, because you don't know where the Bob is, right? Bob could be millions of servers or anywhere in the world, right? Okay, you create a website, then first thing you need is that there must be a public key issued to you, right? You will generate your own public key. Of course somebody will do it on your behalf, or you'll have to do it by yourself. Okay, and then that public key must be certified by somebody. That's in genuinely it's your public key, right? Only then other can use it. So there is a large number of root CAs, and there is a whole hierarchy. There are resellers and so on and so forth who will help you out with it. Okay, for example, if you go to godaddy.com and then get domain name, then they will be a reseller, and they in turn will approach one of the root CAs, etc., and get you certificate. Okay, all right. Or they may issue, they will get certificate from somewhere, and then that must be certified by higher level of CA. Okay, so these public keys are hard coded in the operating system. Public keys of who? All these root CAs, right, and many others. All right. Creating certificates is offline task, right? Okay. So the certificate is created once in advance, then served for user when it's requested. What is the lifetime of certificate? Check. Find it out. This exercise to you. Okay. Okay. So the question is that you start your own domain, say saurabhgupta.com or whatever, right? Who will identify the domain, identities of domain whom they issue certificate? Who is going to do all the checking that this domain is doing good job, right? Or is not a malicious website? Okay. Does your browser check whether site certificate has been revoked? Now, this certificate is issued by some entity that you are going to a server, for example, Amazon.com, and then you are using the public key to transfer some data, but that public key certificate is revoked because of something. So how will your browser know that this certificate, particular certificate that you have in the browser is invalid? So there must be a way, right? Okay. So you'll have to find it out. Okay. So this is the summary. Please go through it. This is what we have studied so far, right? Okay. Now another 10 minutes, we look at some of the application of digital certificates. Now note that we are now switching from, oh, I'm sorry. This is application of digital signature. Not digital certificate application, right? So one application of digital signature was, of course, digital certificate. Because the certificate issued by CA is nothing but based on the digital signature of the CA. Okay. So one application we have already seen. This application we have discussed in brief initially. A software vendor is issuing, software updates, like whatever software you are using legally, okay, you must be getting updates of that. Okay, these updates keep coming up to few years. Once the lifetime of that software is over and software vendor moves to a much higher level version of the software or totally new release, then they may stop sending updates. Okay, so now note that now here something I am telling is not directly connected to the contents here, but why should we have software updates? Anybody? Why should we get software update?
Bug fixing.
Yes, very good. Bug fixing, continuously software, any software will have large number of bugs. So bug fixing is one. But in the context of security, what? See, a lot of vulnerabilities are found every day. Even you can find out vulnerability in code, right? Or something that's available. You type something and the system crashes, for example. It could be because of a bug in software. And once you've got this, you will inform it to somebody. So any software company will continuously get, or software vendor, or those who make application software or system software, they continuously get these inputs about the vulnerabilities from customers and their own team. Okay, and these may be security bugs and normal functionality bugs also. Now, security bugs are very important. They must, now what happens is that these are all published. Whenever there is a security vulnerability, there is a, it's published. You can find out where it's published, right? Now now cyber criminals also have access to that. Cyber criminals know that these bugs have been found. Then why not they exploit this? They can always exploit that bug if it's exploitable. So now what software vendors do, that they provide the fix of that vulnerabilities, security vulnerability, and put multiple of these and then send software update periodically. So there is always a race between cyber criminal and software vendors. Okay, if it's a really critical bug, then the software vendor will do it immediately. If it's not so critical, then they will bundle many of these together and do it periodically after say 2 months or 3 months and so on and so forth, right? Okay, so now this is the reason why you should use a legal copy of software always, because you will always get software updates. Okay, and if you can't do that, then you use open source. Like whatever open source, everything is available in open source, and there also you get software updates. But if you take pirated copy ever, first thing, it may come with lot of viruses or malware inside, and secondly, it will not do software update, because you're when a malicious copy, your copy, which illegal copy is trying to communicate with server, it will come to know about it. Okay, and will not allow software updates, right? Okay, so best is use always legal copies. Okay, so now coming back to this one. Okay, so patches are issued, and then what will they do is that along with the patch or software update, they will have digital signature. Okay, digital signature, they will look at the method. They'll take this content and use secret key, that vendor secret key, and get the signature, and the public key is known to everyone. All clients know the public key of this vendor. Okay, or maybe his vendor has sent it or is published or whatever. or is part of the whole communication mechanism. The public key is known, right? Okay. So basically all this is published in hosting site, and from there client download it, and then they check the signature is correct or not using the public key of vendor, right? So they, in this way it can go to hundreds or thousands of clients, and they can independently verify whether the update is genuine. Okay, malware in between can do middle in man in the middle attack. Now the question I'm asking is that can't we do this Mac? This integrity check can also do, we can do it with Mac, right? What is the difficulty? Anyone? And this is the beauty of asymmetric key encryption also, right? Asymmetric key. Symmetric key, what will happen? Mac is symmetric key, right? Both Alice and Bob must have same key to verify whether contents are correct or not. So now, does it mean that if you are using Mac here in this situation, a vendor will create a key, secret key for each of these clients? Separate key, and then verification will happen. So this is not possible. And even to send the secret key to client, they have to use asymmetric key. Okay, RSA or whatever. You get it? So this works beautifully. Okay. Second is, of course, certificates required by browser. This point we have already discussed. Okay. So for example, your browser is this your browser, okay, is communicating with gmail.com. Okay, and gmail.com has public key PKG. Now, although Gmail is a great company, or Google is a great company, but your browser doesn't know it's a great company, right? Or don't care about it, right? So all it will say is that please give me certificate. So now this google.com or gmail.com has to get certificate from certification authority, and certification authority will use private key or signing key and send the certificate of PKG or Google's Gmail's public key, and then Gmail will send this certificate to the browser. This is how it works. Okay, all right. Okay, this is the flow. So now, as a process of that, this browser will know public key PKG is genuine key because it's signed by CA, and the browser knows CA's public key, so it can verify the certificate. Now, this is the answer of the question I've asked. Server uses certificate for extended period. Say, for example, for 1 year. So these certifications are generally available for longer period. Okay. So when your client browser is communicating in Gmail, the Gmail's public key certificate is available in browser for 1 year. Okay. Okay. Now this is a system that we use is called generally is called domain key identified email. Now what may happen is that how do you know that the mail that you are getting is from gmail.com, not from badguy.com? Okay, so basically badguy.com actually can pretend as gmail.com. How will you know it's is not correct, right? For example, so let's go through this contents, right? Okay. So DKIM system widely used as email signing system on internet. Okay. What is the problem? Problem is a bad email claiming to be from some user.com, but in reality, okay, for example, you are getting an email which is from, say, some user like Ravi Mittals at gmail.com from my Gmail address, right? But in reality, instead of coming from the Google server or gmail.server, it's coming from badguy.com. This is a malicious one. And so it incorrectly makes gmail.com looks like a bad source of email. How do you know it's this? Actually, you are getting genuine one. Okay. So now the solution is that gmail.com signs every outgoing email. Okay. So the organization that generates DKIM generates public key secret key pair. Okay. And uses SK to sign every outgoing email from that organization. Okay. What is that organization? It could be anything. It could be Google, or it could be Windows, or whatever, right? Okay. So the organization places public key PK in DNS domain name server record associated with the organization, so that everyone can read the public key. Now DNS we will study later. An email recipient verify signature on, like your browser, every incoming DKIM email to ensure that email source has been claimed is a claimed organization. If it's a valid signature, the email is delivered, otherwise dropped. Okay, so let's look at this. So what's happening here? This is Gmail user. Okay, and he sends an email. Okay, and then this gmail.com, this server, and it goes to, for example, somebody else. Okay, this is a Bob, for example. This is Bob. This guy is Bob. So the server then signs this email with his own private key. Oh, okay. It got stuck. Okay, all right. Okay, I'm sorry. There's something. Oh, this is my. Give me a minute. There's some problem. Anyway, doesn't matter. This is day number 2 for my new iPad, but stopped working. Doesn't matter. Okay. Well, okay. So now what? Let's continue, and then we'll close in 2 minutes. So now every outgoing mail from Gmail is signed by Google, google.com, using private key. Okay. Now this recipient, for example, you, when you receive it, your browser will have corresponding public key of Google gmail.com. So you can verify. In this way, somebody in between cannot pretend as google.com and send you an email. Okay, all right. Okay, now it started working. Okay. Now, please read through this one. How do you do payment on credit card? I mean, I'm sure many of you would have used this credit card system. Okay, you have credit card. What do? This is point of sale terminal. Like, you go to a hotel or restaurant and then you pay, and then you go to where this machine is. Either nowadays machine works on wireless, so either the person will come to your table and then then you use your credit card, right? How does it work? It's based on symmetric encryption, asymmetric encryption, right? What is this chip? What does it do? So once this card goes inside, now of course that on terminal transaction details are there, how much money you have spent, right? That has to be charged. Then you enter pin, etc., right? So it will do interaction with this, and there will be some communication between the two. Okay, is it encrypted? Check it up, right? The first communication where pin is sent from this machine to your card, is it encrypted or not? That you'll have to. So there must be some pin here, or this pin is not there, it's there in some server. Okay, anyway, there is a big protocol, right? And you must read about it. We don't have time. It's called EMV payment, right? E stands for Euro, M for MasterCard, V for Visa. And there is a protocol here. But there is a use of digital signature. That's important. Okay. So transaction details go to a server and so on, right? It's not that it can be done locally. On flights, of course, there is some technology where you can do local transaction, but actually it comes into effect much later. Now, raw certificates can also be issued. Who will issue this wrong certificate? Because mallory may now in between act as a google.com or gmail.com, but somebody must issue a wrong certificate to her about this fake server in between. Okay. Now there is a number of ways to do it, and one such case study is one such thing happen is by a company called Komodo. So Komodo is one of the trusted root CAs. Okay, so it certifies for any website in the world accepted by every other browser. Okay, it certifies the websites, right, and issues public key. Okay, so Komodo accepts certificate order submitted through resellers because it's a root CA, and there must be hierarchy in between, right? And resellers use program to authenticate. First thing is that reseller must communicate with Komodo, and we have already studied that it has to be authenticated, right? Login or whatever, right? Okay, and then once this reseller submits domain name and the public key, then Komodo issues certificate. Now this was hacked by one Iranian hacker. Okay, so what he has done is that he has hacked into reseller account, and from there he has hacked into Komodo account. Okay, now interesting thing is that the username and password was very simple. Okay, so he wrote his own program submitting orders and obtaining fake certificates. So on March 2011, Komodo issued 9 wrong certificates for popular site mail.google.com, loginlive.com, etc., etc., yahoo.com. And then once certificates are issued, anybody can. So now some server can be created which can be act like google.com. Only thing is that you when you say google.com, your packet must go to this server. It means, and when we type this google.com, etc., it converts into corresponding IP address. Okay, so now this conversion also must be changed from original google.com to a fake google.com, right? So it means that now there is, the domain name server must also be manipulated. So this gentleman, I shouldn't say gentleman, but hacker or criminal could also change the DNS settings. Okay, all right, and then he has sent this kind of message. Okay, there's another break-in. The same guy has also break-in at diginotar.com after some time, right? And the details are also available. So now, security world, you could solve all the problem, like for many problems, like using symmetric key, asymmetric key, hashing. Then we have used digital certificate, MAC, of course, digital certificate, digital signature, digital certificate, and then for that you have a hierarchy of CAs. Okay, and with all this, somebody could find out that you can get, actually certificate can also be certifications organization can be hacked. Okay, so hackers are actually a step, sometimes they these are all very smart guys, right? Okay, all right, okay, please go through this, all the details. And last thing I want you to please go through, this one is very simple, it's called digital envelope. Okay, now question is, an in asymmetric key setting, how to achieve confidentiality, integrity, authenticity and non-repetition. Okay, the answer is digital envelope. Okay, all right, okay, so this is how it works. Alice has a message. Okay, so basically she will use, the message will go as it is. Okay, message is gonna, then she will create a signature using a hash. She will get hash, then she will do sign using her public key. So this becomes signature. She attaches signature to the message. This is a normal practice, right? This is a signature and the message. Now this is in open, right, or in plain text, so this must now be encrypted. Okay, because the confidentiality is lost, right? So now she can encrypt this, all this, using symmetric key. Oh, so of course we are using, not only using asymmetric key but plus symmetric key. Okay, all right, now this symmetric key must be available to other end. So what we can do now is that take the symmetric key of Alice and use Bob's public key and encrypt that and attach this to this encryption. So this is a signed message, and do the reverse here. Once it goes to Bob, he does exactly reverse to get the original message M, which has all these properties now. Okay, please go through this. It's interesting. It's not really you'll find in textbook, but I got it from a paper. So I thought it's this paper. Right? So you can search for this paper and get it. So this is very interesting. Okay, all right. Okay. So thank you very much. See you on Tuesday. I want to have extra class, so please let me know if you can have a class tomorrow or day after tomorrow, Saturday. Otherwise, I will just set it up randomly at some time. Okay. Any question?